Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So, good morning, everybody. It's my great pleasure to welcome John McDonough and his colleagues to Microsoft Research today. This is the first of 4 exciting signal processing-related talks we have after the iWANG 2008 Seattle conference. I guess I first met John visiting Karlsruhe in 2002 or 2003, sharing a common interest of microphone arrays and speech recognition. And he's done a lot of great work related to the CHILL project with large vocabulary speech recognition in difficult environments like parliamentary proceedings and things like that, and meetings and other scenarios. And he moved from Karlsruhe to the University of Saarland in 2006, is that right? Where he's currently continuing this work in distant talking speech recognition. He also has a book on the way on distant talking speech recognition, which we look forward to. And as a side note, he participated in the Speech Separation Challenge, which is one of these evaluations for source separation, and I believe is it the best number? So we look forward to hearing all about that in his talk. So please welcome John.
Okay. All right, so thanks everyone for getting up so early. Thanks, Mike, for inviting me here after I told you I was coming. Okay, so this is sort of an overview talk. I want to talk about a few of the different technologies that we use for speech separation and, in general, distant speech recognition. So this talk will not concentrate on any one single technology. We won't concentrate on beamforming. We won't concentrate on search. We won't concentrate on speaker adaptation. But what I hope to address here is sort of how all of these things are related and how, in order to do good distant speech recognition, you have to get all the little things right. You have to do everything right, not just the thing you like doing. Okay, so we're going to talk a little bit about beamforming and how it relates to blind source separation. A little bit about speech enhancement, a little bit about signal versus multi-channel signal processing, and a little bit about, well, how beamforming is different from speech enhancement, why it's not the same thing, and a little bit about how what are currently sort of separate research communities can influence each other and help each other. Okay, so speech separation. A few years ago, there was a paper by Pera and Alvino, and they spoke about how they can use decorrelation to separate speech, essentially. And they actually looked at 2 beamformers, and they imposed a geometric constraint on the beamformers. And through this geometric constraint, they minimized not the variance of the output of the beamformer, rather they decorrelated the signals. Okay. So we actually learned about this work after we had written a paper about minimum mutual information beamforming. And it was kind of interesting because after we'd gone through all the math, we realized that minimum mutual information beamforming is equivalent or nearly equivalent to this approach by Pera and Alvino if you make a Gaussian assumption. But if you make a non-Gaussian assumption, and speech, by the way, is non-Gaussian, so I'll mention this early because I intend to mention it often. Speech is very non-Gaussian. It's something quite different. Okay. So we've all seen what speech looks like. Okay. Speech is very non-Gaussian. It's also very non-stationary. So this utterance is actually... Is Victor Zhu in the audience? Okay, this utterance is distant speech recognition, spoken by my colleague. Okay, so you can see that during the periods of vowels, you have this highly harmonic structure. You have a lot of energy. In between the vowels, you have much less energy, and it's not periodic at all. Okay. As Mike mentioned a couple of days ago at the talk, during his talk, it's unfortunately the case that when people devise beamforming algorithms, they don't take into account the nature of speech. Okay, we think that's a mistake. We think you should. There's only one important signal, right? We don't care about beamforming for underwater acoustics or sonar or something. Speech is the important signal, right? Let's take into account what speech looks like. So, in addition to being very non-stationary, speech is also highly sparse in the subband domain. You can see that here, right? So, especially during the fricatives, the consonants, you can see that speech is very sparse. But it's also sparse during the periods of voice speech. Why? Because during the periods of voice speech, you have a harmonic structure. Okay, so if a subband lies on a harmonic, it's going to be strongly excited. If it lies between the harmonics, it will be essentially not excited. Okay. Already said this. All right, so what we've looked at recently is trying to model the characteristics of speech. And one of the first characteristics we looked at was the non-Gaussianity of speech. Okay, speech is not a Gaussian signal. So we wrote a paper a few years ago, it's recently appeared, and we looked at modeling speech with these so-called Meyer-G functions. Okay, Meyer-G functions are quite nice because they allow you to extend the univariate PDF to higher order variates. All right. So it turns out, though, that you can do probably even better speech modeling if you use something called the Generalized Gaussian Pdf. So the Generalized Gaussian looks like this. So if you set here, p is the scale factor. If you set p equal to 2, you'll have the generalized, the regular Gaussian. Okay. If not, you have this normalization factor here that ensures that this sigma term is in fact the square root of the variance, i.e. the standard deviation of your PDF. Okay. You can solve for this normalization factor as such. So what's interesting about this is that by setting p to be less than 1 or less than 2, you can get a very super Gaussian structure, or PDF structure. So here is what the PDF looks like for various different values of f. So you can see that for 2, p equal 2, you get the Gaussian. For p equal 1, you get the Laplacian. Okay? But where things become interesting is when you set p less than 1, because in this case, you get a very super Gaussian structure. Okay, so your kurtosis increases every time you lower p. Okay? So you can see that for a very low value of p, you get a PDF with a very high kurtosis, which means you have lots of probability mass in the center, not so much in this intermediate regions, but then lots of probability mass out in the tail as well. And this is what speech looks like. So in this plot, what we did was we actually estimated the optimal value of p, or this shape factor, on a set of training data. And we've plotted this optimal value of p globally for different values of, for different frequency levels. So what you can see here is that, first of all, okay, this is the shape factor actually, the scale factor. So you can see that, as we all know, speech is mostly concentrated, the energy in speech is mostly concentrated in the lower frequency levels. What's interesting, though, is that speech is fairly non-Gaussian in the lower levels and becomes closer to Gaussian in the higher levels, higher speech levels, or higher frequency levels. So here is a histogram that demonstrates quite clearly that speech is not Gaussian. So you can see here in the green is the actual speech. Okay, this is what we modeled from the training data. And you can see that speech is not at all well represented by a Gaussian distribution. The Gaussian distribution is this one. It's represented better by the Laplace, still better by the gamma distribution, but best of all, so far, by this super Gaussian density, by this generalized Gaussian density. Okay, so it's kind of interesting that speech is not a Gaussian signal. Or actually, it sort of stands to reason. If you know anything about the independent component analysis literature, then they claim that every signal that's interesting, i.e. every signal that carries information, is not Gaussian. Okay? Why is it not Gaussian? Well, this might not be exactly their explanation, but this is sort of the way I understand it. First of all, the central limit theorem says that if you add enough independent random variables together, regardless of their distribution, the sum will be Gaussian. Okay? But in modeling speech, we don't care about the sum of independent random variables. Rather, we care about one single independent random variable, namely the speech. That speech is highly redundant, okay? And that means that it will not be Gaussian, okay? You can think of a Gaussian random variable as somehow being, well, either the most informative or the least predictable of all possible random variables. It's the most informative because it has the highest entropy of all random variables for a given variance. It's the least predictable because it has the highest entropy of all random variables for a given variance. So real signals, i.e. signals that carry information, are redundant, and this redundancy makes them predictable. Okay? We don't need to convince anyone here that speech is predictable. Okay? It can be coded. Its bit rate can be reduced. Right? So, speech is not Gaussian, as I've said. Not Gaussian. Okay, this is okay. So I'm sure we're all familiar with this this little presentation here, where if we take enough random variables and add them all together, the PDF becomes Gaussian. So you've all seen this before, I'm sure. So here's a little MATLAB script I put together. You can see that the very pointy Gaussian, or the very pointy PDF, is actually the Laplacian. And if you add together enough of those Laplacian random variables, you eventually approach a Gaussian. So you can see that the very thick blue line is actually the Gaussian random variable. Okay? So here's in the linear domain. Here's in the log domain. So you can see in the log domain, the tails are eventually approaching the Gaussian. All right, so it sort of stands to reason speech is not Gaussian. Here again are more histograms of speech. And what you can see here is that when speech is reverberated, or corrupted by reverberation or by noise, it becomes more Gaussian. Okay, the central limit theorem says it should become more Gaussian. So, what we've looked at in the past few months or years is actually how we can make use of this fact that speech is not Gaussian, and that it becomes more Gaussian when it's corrupted by noise or by reverberation in order to do better beamforming. So we started with a generalized Seibel canceller, and we've all seen this before. Here's the input to our beamformer. Here's our quiescent weight vector, our blocking matrix, and our active weight matrix. And then, in addition, we might have a post filter, okay, on the output of the beamformer. Entropy is a basic quantity from information theory. It's a measure of pure information. Okay? So, here is the definition. If I take the log base 2, then I'm measuring entropy in bits. If I take it in log base e, i.e. the natural logarithm, I'm measuring it in nats. Okay? But one way or another, this definition of entropy is a measure of pure information. Okay? The more information I have, well, the more I learn every time I see this random variable, but the less predictable this random variable is. The Gaussian random variable is the least predictable random variable. Other random variables are more predictable. So, there's a well-known measure of non-Gaussianity from the field of ICA. It's called neg entropy, and all it amounts to is the difference between the entropy of a Gaussian random variable and a non-Gaussian random variable. Okay, both have the same variance, but one is Gaussian, the other is not. You can liken this to also, if you put this into that equation, you can see that quite obviously it's the expected value of a log likelihood between a Gaussian random variable and a non-Gaussian random variable. There's also another well-known measure of Gaussianity, namely kurtosis. Okay, so super Gaussian random variables are actually called super Gaussian because they have positive kurtosis. A random variable has zero kurtosis. Sub-Gaussian random variables have negative kurtosis, and super Gaussian variables have positive kurtosis. Okay, here's the definition of kurtosis. And generally, as the kurtosis of a PDF increases, you're going to see more probability mass concentrate around the mean, more move out into the tails, and less probability mass in the intermediate areas. Okay, so super Gaussian random variables are characterized by infrequent but large deviations from the mean. All right, so this sort of stands to reason. If you think about speech, speech is largely periodic. Not all of the phonemes are periodic, but the vowels are. The vowels have the most energy. So if you think about that spectrogram that I showed before, you saw that during the portions of voiced speech, you have these harmonic structure. Okay, so if a subband falls directly on a harmonic, it's going to be very strongly excited, i.e., the values are going to be far, far away from zero, or far, far, far away from the mean. If it falls between harmonics, it's going to be as good as not excited. Okay. Okay, so most of the field of, with a few exceptions, one of the exceptions I already mentioned, i.e. that the work of Pera and Alvino, but most of the work in acoustic beamforming was taken over more or less directly from earlier work in beamforming. And the earlier work in beamforming was done for microphone, not for microphone arrays, but for antennas, underwater sonar, etc. Okay. Most of the assumptions made in that earlier work do not apply to acoustic beamforming. Okay. Because most of those assumptions were formulated for signals that propagate in a more or less free field. Okay, so Walter Keller might argue with me here, but my view is that those assumptions that were made for conventional beamforming really don't apply to acoustic beamforming. Why? Because in acoustic beamforming, the two biggest enemies are noise and reverberation. So, when I clap my hands, you hear the room ring down. Long after my hands have come together, you hear that sound perpetuate. Yes, that's reverberation. That's the big enemy. It turns out that humans are very good at dealing with this reverberant environment, such a reverberant environment. In fact, the human auditory system is such that the intelligibility of the speech increases when it is in a reverberant environment. Okay, you probably realize this if you've ever been in an anechoic chamber. You realize that it's harder to understand someone talking to you than if you're in an environment like this. The reason for that is because the human auditory system is such that it can use the early reflections, i.e. the reflections from the walls and from the windows and so forth, that occur within 50 milliseconds of the first onset to increase intelligibility. At the moment, we don't fully understand how to make our automatic speech recognition systems do this. Okay? This is what we have to learn. This is why automatic or distant speech recognition is still an unsolved problem. There are some people that would say, well, speech recognition, that's a solved problem. I can go to Egghead Software and I can download Microsoft Vista. It has speech recognition, right? Not like this. Okay, so what we've actually looked at, in Trento, we presented a paper showing that you can actually use neg entropy as an optimization criterion for beamforming. And in fact, when you use neg entropy, it works better than any of the other standard techniques. It works better than anything based on minimum variance distortion response or minimum mutual information. Oh, sorry, it works better than MMSE, i.e. better than minimum mean square error. Yeah, it works better than techniques based on those two approaches. So in maximizing the neg entropy of a beamformer, what we're actually trying to do is to restore the non-Gaussian characteristics of the original clean speech, i.e. we know that speech is non-Gaussian. Its PDF is non-Gaussian. So in maximizing a neg entropy criterion, we're trying to eliminate the distortions caused by reverberation and by noise, which tend to make the speech more Gaussian. Okay. It so happens that in order to use the neg entropy criterion, as I've shown before, you actually need to know what the PDF of the speech looks like. You see it comes into play here. So this is not really a problem because, well, anyone doing speech recognition research has hundreds or thousands of hours of speech data online. So it's not so difficult to estimate a criterion or estimate this PDF. If you assume if you make an assumption that the PDF is characterized by a parametric model. If you want to really estimate the PDF of speech, that's more difficult because, of course, then you have to use your characteristic function, estimate all the higher order moments, et cetera, and then it becomes much more difficult. It turns out, however, that you can use also kurtosis as a maximization criterion. Okay, we actually have a paper about this at InterSpeech next week. And the nice thing about kurtosis is that you don't need to know the PDF. You just need to know the second order moment and the fourth order moments of the speech. Okay. By the way, I didn't do this work. This work was done by Kenichi Kumatani as well as my colleagues here in the audience, Friedrich and Barb. Okay. So we actually looked at a simple model of what happens to the speech when we use kurtosis as a maximization criterion or an optimization criterion for beamforming. So we took a very simple example where we have one source, a wall, i.e. a sound reflective surface, and then a microphone array. So, as you all well know, when you have a simple MVDR beamformer, of course it's going to try to null out any source coming from anything but the look direction. Okay, this leads to the well-known signal cancellation problem. It's kind of curious, though, that if you take neg entropy as an optimization criterion, it's not going to try to null out any source coming from anything but the look direction. Rather, if you have a source coming from something other than the look direction, and it's strongly correlated with your desired signal, we'll try to amplify it. Okay? It will try to amplify it because, of course, in the subband domain, a delay manifests itself as a phase shift. This phase shift can be compensated for by simply setting the active weight vector correctly. Okay? So, because you're trying to maximize a neg entropy criterion, you're trying to make the signal as non-Gaussian as possible. This is what the neg entropy criterion tells you, how non-Gaussian your signal is. You get a non-Gaussian signal by adding up the same portion of the original speech, because the original speech is very non-Gaussian. You get a Gaussian signal, on the other hand, by adding up what are essentially independent portions of the same signal. This is why speech becomes more Gaussian when it's corrupted by reverberation or by noise. Okay? So anyway, what you see here in this plot is evidence that with a neg entropy criterion, you don't suffer from signal cancellation, which is the primary problem with the conventional beamforming criterion. Rather, you have here signal amplification. If the signal comes from some direction other than the look direction, it's still the same signal. So here you will try to amplify it. So here are a few ASR results, which is what everyone cares about. Not about simulations or any theoretical arguments. This is what you care about, right? So you can see quite clearly that the maximum neg entropy beamformer does better than the delay and sum beamformer, better than the delay and sum beamformer with a post filter, and better than the MMSE beamformer, the minimum mean square error beamformer. Okay. You'll notice, though, that the maximum kurtosis beamformer does pretty well. It's not quite as good as the minimum neg entropy beamformer, but it's still pretty good.
Quick question. Are this running the adaptation in batch or online?
We did everything in batch. So these are actually four passes of the speech recognizer. So the first pass is completely unadapted. Second pass uses VTLN and feature space adaptation. Third pass uses VTLN, feature space adaptation, and MLLR. Fourth pass uses VTLN, feature space adaptation, MLLR, together with a speaker adapted training model. So still stronger acoustic model.
The beamforming part is batch.
Yeah. So we haven't tried yet to develop an online algorithm. So we're just processing the entire, it's utterance by utterance, but it's still batch, yes. What's interesting is that with the conventional beamforming techniques, i.e. MMSE, you actually have to beamform only during the silent portions of the speech, i.e. when the speaker is not speaking. Otherwise, it doesn't work. For the maximum neg entropy beamformer, we beamform on the entire utterance. We don't care if it's silence or if it's during speech. Okay. So, here I wanted to talk a little bit about, Here I wanted to talk a little bit about what Mike Seltzer had done, and this sort of borders on what Barbara presented yesterday, or the day before yesterday at iWank. If you look at this diagram, speech, our time frequency plot, you see, of course, that speech is very non-stationary. We all know this. So you have a lot of energy here during the vowels. In between the vowels, during the consonants and the fricatives, etc., you have very little energy. So what Barbara has looked at recently is trying to use the hidden Markov model to model this non-stationarity. Okay? So what she has done is said, well, we're getting a nice improvement by looking at using this neg entropy criterion in order to model speech, okay, and trying to restore the non-Gaussian statistics of the original speech. But what we ignored so far, or prior to this work in any event, is the fact that speech is non-stationary. Okay? It has very different energy levels between vowels and fricatives or consonants. So what she has done is actually we've taken the first pass of the beamforming, done speech recognition, extracted a Viterbi alignment from the speech recognizer, and then taken an auxiliary model that has the same context-dependent information as the model we use for speech recognition, and then aligned that with the utterance. And then based on this auxiliary model, we've been able to back out the power spectral density for any given short-time feature of speech. So then we've actually used this short-time change in the speech energy in order to do better beamforming. Okay. And as you recall from the presentation a couple of days ago, this actually yields a further improvement in a further reduction in the word error rate. So what Barbara has done so far is to take into account the non-stationarity of the second-order statistics of the speech. What we want to do next is to take into account the fact that not only the second-order statistics are non-stationary, but also the higher-order statistics. So we want to make both the shape factor and the scale factor dependent on the short-time characteristics of speech. Okay, so what I said at the outset, unfortunately I didn't have time to prepare slides to illustrate this remark. But in our experience, if you want to do better distance speech recognition, it's very, very important to do all the little things right. Okay, we've seen that innumerable times in our recent work. Okay. So if you were there on Monday or Tuesday, you probably remember that I was asking many questions about which filter bank are you using. It turns out that the filter bank that you use in order to analyze your speech is extremely important. Okay? At the start of all of this, we were using the wrong filter bank. We were using a filter bank that was optimal for subband coding of speech. It turns out it was not optimal for adaptive filtering or for beamforming. So it took us, we were sort of starting out. We had no expertise in filter bank design. So it took us probably better part of a year to realize that, the filter bank that we were using was actually masking gains that we would have otherwise had by improving our beamforming or by improving our post-filtering. Okay? It's also very important to optimize your recognition engine on the data that you actually want to recognize, i.e., building a recognition engine or building an acoustic model that's really good for close-talking data. Data from a close-talking microphone is not going to give you the best performance for your far-field task. Okay? It's also really important to work on real data. We learned this the hard way, because when we started out doing this, we were working on data that was artificially convolved. All right? So we were thinking, wow, we're doing really good on this data. We can do almost nothing at all. We can do delay and sum beamforming and our standard speaker adaptation tricks, and we're within 2% of what we get with a close-talking microphone. Then you try it on the real data, and you find out you've made no progress at all. So, yeah, in short, you have to do all of the little things right in order to do good far-field speech recognition. That includes the speaker tracking as well. Okay. All right, so going to finish up a little bit early. Do we have a web browser? I wanted to play an audio sample.
Yep. Escaping out of that. Oh. Oh. Maybe this. I don't know if you can you use that?
Okay. All right, so how do I get back to the desktop? Okay, got it. No.
You want that open?
Yeah.
Your PowerPoint, I think, is there.
Yeah. Okay.
Do you want to play this one?
Yeah. All right, so here's a little, this is the only thing that I prepared that approaches a demo. So here is actually a segment of speech from the Speech Separation Challenge. So this was organized by Mike Lincoln, who's at the University of Edinburgh, and he actually collected data from the WSJ 5K task, Wall Street Journal 5,000 word speech recognition task. But unlike the standard Wall Street Journal corpus, this data was read by speakers who were standing several meters away from the microphone array. So it was collected with a circular microphone array, actually 2 circular microphone arrays of 20 centimeters in diameter, 8 channels. So the speakers were speaking simultaneously.
The matter of a public offering was discussed at the firm's annual partners gathering, which met yesterday. Might announce the stock buyback.
So everyone understood what the second woman said, of course. Mike Seltzer, what did the second woman say?
The matter of a public offering was discussed at the firm's annual partners gathering, which met yesterday. Might announce the stock buyback.
Something about the stock market losing 500 points in one day or something like that? Okay, let's try this.
The matter of a public offering was discussed at the firm's annual partners gathering here Saturday.
So this is what comes out of our beamforming. After MMI beamforming, minimum mutual information beamforming, we also use a technique called binary masking, which was also discussed during iWank.
The matter of a public offering was discussed at the firm's annual partners gathering here Saturday.
It turns out that because speech is so sparse in the subband domain that you can actually use a binary mask to separate the speech, i.e. you can look at, you can compare the outputs of the 2 beamformers and see which one is louder in any given subband, and then set the other one to 0, which is in fact what we do. And you can see
the matter of a public offering was discussed at the firm's annual partners gathering here Saturday.
That's without the binary masking. The binary masking actually really improves the separation.
The matter of a public offering was discussed at the firm's annual partners gathering here Saturday.
Unfortunately, it introduces artifacts.
The stock moved up 2 3/8 Monday on expectations that the company's board, which met yesterday, might announce a stock buyback.
So you can hear the sort of burbling underwater effect. In any event, we're still working on this.
So are that's first, second, and fourth essentially equivalent except for filter range?
No, essentially these are more or less equivalent. These 2 here are equivalent except for the binary masking. So here's the original single channel of the microphone array.
The matter of a public offering was discussed at the firm's annual partners gathering, which met yesterday. Might announce the stock buyback.
So there you hear essentially no separation, and this is with the MMI beamforming as well as the binary mask.
The matter of a public offering was discussed at the firm's annual partners gathering here Saturday.
Here's the same thing without the binary mask.
The matter of a public offering was discussed at the firm's annual partners gathering here Saturday.
So in this one, obviously, the second voice is still audible.
Right, I'm trying to figure out, is there something you could play that would show differences in filter bank only?
No, I don't have such audio samples, but there is a significant difference. So I mentioned before that when we started out doing this, we were using the wrong filter bank, i.e., we're using the perfect reconstruction filter bank. So you can see the difference in word error rate. Okay, it turns out that when we were using the perfect reconstruction filter bank, we got no improvement. In fact, we got a degradation by applying a post filter. But with a filter bank that was designed specifically for beamforming or adaptive filtering, you see that we get a healthy improvement by doing post filtering. Okay. So it's, well, we probably don't have time to go into this, but the perfect reconstruction filter bank is called perfect reconstruction because, well, it gives you perfect reconstruction provided you don't change the subband amplitudes, i.e. you don't do any beamforming or adaptive filtering in between the analysis and the synthesis. It gives you that because it's based on a concept of aliasing cancellation. So the perfect reconstruction filter bank is a maximal decimation filter bank. That means if you have m subbands, you're decimating at a factor of m. Okay? It only works because the aliasing that is present in one subband is canceled off by the aliasing that's present in all the other subbands. But as soon as you start mucking around with the subband magnitudes, this no longer works. Okay? So Walter Kellerman knows, of course, about this. So it's kind of funny because, yeah, filter bank design is an old science, but people realized relatively late that filter banks were good not only for subband coding, but also for adaptive filtering and beamforming. That's why, although the filter bank design is old, the good designs for adaptive filtering and beamforming have only appeared recently, i.e. since the turn of the century. Okay. So in any event, as I said, it's important to do all of the little things right. It's important to look inside of the black boxes. You can't just say, okay, I have a filter bank. It's as good as any other filter bank. Or I have overlap add. Yeah. Overlap add does even worse than any of these filter banks, oddly enough. Okay.
And for the feature extraction for this, I mean, did you go from the, so if you went back through the synthesis filter and then did feature extraction? Because you could also just extract features right out of the output, right? Yeah,
you could.
Then, I mean, then would this gain issue be as much of an issue?
In theory, you could do that. I mean, for speech recognition, we do everything based on the frequency domain representation. I mean, we put a Hamming window on the speech, and then we take a FFT. Yeah, unfortunately, it's not quite as simple as that. So I don't know how to do what you're suggesting, because for beamforming, you need really good frequency resolution. Okay, for speech, you don't need such good frequency resolution. Rather, you need good time resolution. Okay, that's why, in fact, when we do beamforming, or rather when we do analysis for speech recognition, we smear out, essentially, the frequency resolution. We put these Mel filters on top of it. You know, we don't care about what exactly happened for the frequency resolution. So, for those reasons, we don't yet know how to go directly from sort of the beamforming frequency representation to a representation that we can use for ASR. We have to go back through the synthesis filter. We have to resynthesize the output.
So what do you end up with on the output of the beamformer?
What you heard?
How many frequency bands and how many subbands?
Well, we end up with a time signal.
But I mean, if you stop, I mean, how many subbands are near adaptive?
Okay, so we typically use, what, 256 subbands? So we're looking to increase the number of subbands because if you think about it, the number of subbands that you actually use is related to the length of the filter that you're applying to each of the outputs of the microphone array. Okay, so it's kind of strange because To do better de-reverberation, we would like to increase the number of subbands because we would like to have a longer filter so we can de-reverberate the signal better. On the other hand, for speech recognition, we would like to have shorter subband, or smaller number of subbands. Because there, in speech recognition, as I mentioned, you're trying to do better, you want better time resolution. So right now we're using 256. We want to increase the number of subbands. We've also thought about, okay, so currently for our beamforming, we're using only one single subband block. We've also thought about doing multiple subband blocks, sort of like what Walter Kellerman and Armin Sayre are doing, to try to account for the fact that you have this fairly long delay between the arrival of the direct path and the reverberation, the early reflections. We've also thought about using a particle filter to actually account for the late reflections. Okay, because in the late reflections, essentially what you have is a diffuse noise field. And several people have shown, researchers at NTT have shown that you can actually use multi-step linear prediction in order to account for this late reverberation when the reflections are essentially so numerous that you can no longer distinguish individual reflections. You have a diffuse noise field. Okay. All right. Any other questions?
Thank you, Joe.